So this video is going to discuss networking for PLCs. We'll look at various different types of PLC networks, and then we'll talk in detail about Ethernet, including discussion of the OSI model, encapsulation, the 7 different layers of the OSI model, the 4 layers of the TCP/IP model, and IP version 4 addressing and subnet, and also some security and networking devices. So what do we need protocols for? Well, if you look at this picture here I found on the internet, we know that you're supposed to be driving down the road on the correct side of the highway, whether that's on the right side in the United States or on the left side in England. But here you can tell looks like traffic is really backed up, and so a lot of these cars decided they're just getting off no matter what way, and that obviously just causes pure chaos. So we need protocols to establish the way things should be done so that communication can be done in an effective and efficient manner. So when we look at a standard PLC, such as the ControlLogix PLC, there's lots of different types of networking that it can do. It can use something called the data highway. It can just use remote I/O. It can use Ethernet/IP. It can use ControlNet. So and this just you will need a separate card or module within the PLC to be able to handle each one of these different types. But one PLC could at least theoretically communicate on virtually all the different types of networks simultaneously. So as I say, you'll have to put a separate card in the slot for each one. So when we look at the different types of communication modules that are available, and this is not necessarily the complete list, but these are probably the most common. So number one, we have up here Ethernet/IP. Now, a lot of times you see IP, you think Internet Protocol, but actually when it's written like this is actually a special subset of Ethernet for industrial protocol. So Ethernet/IP in this context actually refers to a dedicated subset of Ethernet specifically for industrial communication between PLCs and other devices on a network dedicated for manufacturing or some sort of production. Other networking that are specifically for actually the rest of these pretty much here, ControlNet, DeviceNet, Circos, all of these have been developed specifically for communication between controller type devices and I/O in a industrial type network. Okay. One of the big things to kind of note here is that the Data Highway Plus, which is actually kind of an older protocol and just plain remote racks, these are proprietary. They basically only work with Allen Bradley type PLCs, where these other protocols are all open, meaning that any manufacturer could build a sensor or something that could communicate on this network and therefore communicate with a PLC or other device attached to this network. Alright, so let's look at Ethernet here. Ethernet is supported for pretty much all the modern PLCs. are going to support Ethernet, and therefore will probably be able to support the Ethernet industrial protocol or /IP that I referred to earlier. Ethernet is actually seeming to become more and more popular for industrial networks because the hardware for Ethernet devices is used all over the place, and so the price of it has dropped dramatically in comparison with the dedicated control net or device net type hardware that only is for industrial type networks. Okay. But one of the major concerns though with Ethernet is the fact that because it's used throughout the world and the internet, that we do have to keep in mind security. I mean, we need to keep security in mind for all types of networking, but for Ethernet specifically, I think it's even more important that we consider that. So for one thing that you really must do, in my opinion, is your industrial network must be a physically separated network than your office network, and should not have internet connection unless you absolutely have to for a certain application. But if you do, you need to make sure that you have proper security in that connection. Another kind of shortfall of the Ethernet protocol is Ethernet protocol was never designed to give you what's considered real-time communications, which is very important when you're talking about, okay, here's this PLC and it's in control of a motor that's filling up an acid tank. And when that acid tank gets filled, we need to make sure that we shut it off before the acid overflows over the top and the pressure gets too big and the tank bursts or something along those lines. So it's very important that when that sensor tells us that, hey, it's full, we need to stop in a timely manner. So if somebody, comes along and says, oh, I'm going to download a video on this network and just start watching a video for a few minutes, and then I'm sure you've all experienced like watching videos and you see the little buffering sort of messages, and so and that's fine for people surfing the internet, watching videos and things like that. If you have to wait 30 seconds or something for a buffering and because there's so much communications on the network. But when you're talking about getting that information from a sensor to the controller back to the actuator to tell the motor or pump to stop, that needs to be done in a timely manner. And so that's why they built the Ethernet/IP protocol, to try and compensate for the fact that the original Ethernet protocols never really had any real-time guarantee. How long is it going to take for the message to get from one device to another, where most of the other protocols that we are going to discuss here actually are dedicated to guarantee that real time. So again, the industrial protocol here, it was modified slightly, so it's still Ethernet. It follows all the standard Ethernet protocols, but it has kind of a subset of specific ones to help guarantee that the messages are going to be sent in a timely manner. All right, but it's still not 100% a guarantee that it's going to get there, because the switches and stuff that it may have to travel through aren't necessarily going to guarantee that. So if we look at something like ControlNet is a fairly new version for performing remote I/O. It does high-speed transfer of communication, and it it was, when it was designed, dedicated for control type systems, and therefore it has in the protocols the guarantees so that the time critical information can get delivered in a timely manner. So we know that within so many milliseconds that packet of information is going to be sent across the network. Similarly with DeviceNet, DeviceNet is just a different protocol developed by some different companies, but it was opened up so that any company can build devices to communicate on this network. But again, it was designed for that real-time communication, but it can't handle quite as much data as, like, say, the control net. Serial or SERCOS stands for Serial Real-Time Communications System, and this again is this has it built right into the name, real time. So SERCOS is, as you can see, it's guaranteed to provide that information. The other thing about SERCOS is the fact that because of all the noise in a factory, the SERCOS was designed to work using fiber optics, and so therefore it does an excellent job of rejecting any noise, because noise from cell phones or other electronic things don't really enter in and get into the fiber optic cables, so where they would a standard copper cable. So this helps reduce noise greatly. Data Highway Plus is an older one. This was a proprietary network for Allen Bradley's. It would allow multiple PLCs on the same network, and they could send data back and forth. Okay. Remote I/O is really not necessarily a network, but it's just where you would insert into your primary PLC a dedicated card that would then run out to a rack, to a separate chassis that could have more I/O. So if you had your Control Logix chassis and you had 17 slots, and all 17 slots were full, but you still needed more I/O, you didn't necessarily have to buy a second PLC and then create a second program for that second PLC. You just buy a remote rack card and then the remote rack and the extra I/O, and so you have one PLC doing the communications, but it's just you utilizing more I/O than could fit in the standard chassis. Okay, and the traditional one, the one that's kind of been around forever, is just plain serial communications. So serial communications means one bit at a time, which means that it's very small amount of information can be transferred in a timely manner compared to the other networks that we discussed. But it's very simple, and you can use it for virtually any device, that as long as that device can do serial communication, which is just a 2-wire setup, and you can transfer that bit of information a long distance over to a PLC. Alright, so if we talk about Ethernet cables specifically, Ethernet requires what's called the Cat5 Category 5E, that's revision E wire, or the newer Cat6 cable. Now both of these are 4 twisted pairs, so there's 8 conductors in a cable. So remember, the definition of a cable has more than one conductor within the outer insulation. So we have 4 twisted pairs. They twist the pairs together to help reduce the crosstalk between those conductors. Cat6 also adds this extra insulator piece in the middle to keep the 4 pairs isolated from each other to minimize even more crosstalk. So Cat6 has this extra separator in the center of it, number one, and number two, it has the wires are twisted tighter or more with more twists than the Cat5 cable. So Cat5 is rated for a gigabit or 1,000 megabits per second communication. It's relatively cheap and fairly easy to work with. It's good up to a length of 100 meters. Okay. Cat6 actually is good for up to 10 gigabits. Okay, as long as you're for a smaller distance, so only about 33 to 55 meters. If you start getting over that 33, you may not be able to guarantee that 10 gigabit distance. At that point, you probably want to be switching over through a fiber optic type connection. But Cat6 is a little more expensive. Obviously, it's a little more difficult to work with, but it has a higher signal to noise, which is why you can do a higher speed with that. So, and it also tends to have slightly smaller wire gauge in it. All right, so at the ends of this Cat5e or Cat6 cable, we are going to have a RJ45, where RJ simply stands for registered jack. So an RJ45 connector. And when we connect that, remember that we've got 8 conductors which are in pairs. So those pairs are color coded. So you have a 568A wiring based on the color codes and a 568B. And so if you look at the connector and you see the green, white, and then green on the left, that means that that's a 56A connector. If it starts with an orange, white, and an orange right there on the left, then that tells you it's a 568B. Most of the wire, if you go out and buy one, most of them are going to have the 568B wiring. Okay, and that wiring would be usually on both ends. Okay, if they've got the orange, white, orange on both ends, so you got 568B connections on both ends, that's considered a straight through cable. If you have the 568A on one end and 568B on the other, that's considered a crossover cable, because the two of the pairs, you see the green and the orange are swapped between the 568A and 568B. The reason for that is that you basically have a transmit and a receive. Now, it's very important that you understand this, because if you are connecting your PC and your PLC together through a switch or a hub device, then you must use the straight through cable. You can't use a crossover. However, let's say that you had your laptop and you wanted to walk out onto the plant floor and download an update to the PLC program. So you're just going to plug in directly from your PC directly into the PLC. Well, if that's the case, you need the crossover, because one of the jobs of that switch is to receive through. So like, let's say the orange is transmitting from the PC, so the PC is transmitting on the orange, and then it sends it to the switch, and then the switch then forwards that over to the PLC, and it basically does that crossover. That's one of the things like the switch kind of does, is the crossover piece. But if you're wiring the PC directly into the PLC without a switch in the middle, you must have that crossover cable. All right, so when we talk about communications, the first thing we need to do is think about various different rules. Okay, so depending on what kind of communication you're going to do, number one, you may have punctuation. Obviously, if we have written language, we have punctuation. If we're communicating orally, the volume or the level of our voice kind of indicates messages. Body language can send messages. All right. So when we're communicating, though, we've got to have these rules. So the term usually people refer to as a protocol. But what is a protocol? A protocol is the rules that have been set up that are intended to be used when you are communicating between two devices. Okay. Some of those rules specify like how big of a packet of information can be sent at one time, how fast can it be sent, what happens if you're trying to send to the PLC and the PLC is trying to send back to you. At the same time, that's kind of what they consider a collision. Two different devices on the network are trying to transmit at the same time. What do you do about that? Right? So these are all rules that have to be addressed. And so the protocols, depending on which protocol you're using, they have set rules to address these issues. Right? This slide's just showing a kind of an interesting little video here. There's this video of it was taken, I think, in 2012, so it's actually kind of gotten a little old now, but it's very interesting to watch this. It was done like a couple days before Christmas, and they sent a pie through FedEx to from the East Coast to Hawaii. And they're just kind of showing how FedEx handles the massive amount of packages that they handle in a single day. And it's just very interesting. If you watch this video, the link is up there, and when you watch this video, you'll see these packages are just flying through there. So like you see right here on the bottom, I've got this package was just flying down this conveyor where this white box is, and all of a sudden this arm just whips out and pushes this box down in this chute and sends it off this way so that it'll be loaded onto the correct plane and hauled wherever its destination is. Okay. So you may want to watch that video. It's just very interesting to kind of watch and think about how these PLCs controlling those miles and miles of conveyor are set up. Okay. All right, so when we want to send some data, like if we're sending temperature, let's say we had a temperature sensor and it's telling us that it's 75 degrees Celsius, and we want to send that out up to the PLC. Well, if we're doing that across the network, we have to first take the data, which is the 75 degrees Celsius, and we have to encode that so we can put it out on the network. So just like if you were going to mail a letter to a friend, you would have to take the letter, which is the data, put it inside an envelope. On the envelope, you're going to have to put their address. You're going to have to put your your reply address on there, and then you're going to have to put a stamp on it. So all this is kind of what was kind of considered encoding. When we talk specifically about sending data on a computer network, there's actually kind of several layers of encoding, which we'll get to in a minute. So when we get down to the hardware level, we're sending pulses. So we're either going to send electrical pulses along the conductors of the wire, or if it's Circos or some other fiber optic communication, we're going to be sending pulses of light. So we have to kind of keep track of how are we sending those and how fast are we sending those. And, or if whether we're sending it across a radio or a Wi-Fi type connection. So the data needs to be as encapsulated into like the envelope. As I said before, we take the letter, we're going to fold up that letter and slip it inside of that envelope, which has an address on it. So that is the encapsulation piece. So the data is inside of there, and then we're going to put on top of that extra information such as the addresses, and we're also going to do something called checksums, because when we send the information, we want to make sure that the information was received properly on the other side. And so if it wasn't received properly, we're going to run a checksum on it when we get the data, and if the checksum doesn't match the sum of the bits within the data, then we're going to send back and say resend the data. We're going to request that the data be resent. Alright, so this slide's just trying to kind of show a visual method of sending or performing the encapsulation of the data. So the first thing we're going to do is we're going to take the data, and then we're going to put it on what's called a transport header. Okay, and the transport header is for the transport layer. And then there's a network header, and then there's a frame header. All right. So like let's consider you're going to send your letter not just down the road, but you're going to send it say to somebody in the military who is overseas. All right. So the transport header could be kind of considered, say, the street address. Okay. And then the network header would be like the zip code, which would say the city. And if you were sending it actually like overseas to an FPO type address, to send it to somebody overseas through the military, then you would add on like the FPO address information in there. So each one of these is kind of like different bits of information. Right. So if we look at the OSI layer, you see that they actually break it down into like 7 layers here. So we have the application layer, the presentation layer, the session layer, the transport layer, the network layer, the data link layer, and then the physical, where we got to the encoding of the binary pulses on copper or light pulses on fiber optics. All right, so there's all these different layers. Now, if we look at a little simpler model, what they basically do here on the simpler is they have the application layer. And so the application layer there is effectively the data. And then we send that to the transport layer. And then we send it to the internet layer. And then we send it to the hardware. So the way that kind of works is if you look at the Ethernet card, the wire, the cable that you're going to connect, that's sending those pulses. Okay, so this is the hardware layer that's just going to send those pulses out to the switch or to the device that your PLC is connected to. If it's connected directly to the PC through a crossover cable, then it's just the pulses it's sending directly to the PC. So that is that encoding of the actual data. but that data includes the addresses. So we have the IP, which is the Internet Protocol. In this case, we're talking about just the Internet Protocol, which is an address, which again you might kind of consider, if you consider like classes here at Stark State, at the college, the Internet Protocol would be like the address here at the college. So it would be like 6200 Frank Avenue, North Canton 44620, you know, whatever the address is. And then what room number are you in? So what class are you in? What's the room number? Once you get it to the college, where's it going inside the college? And so that's kind of this transmission control protocol. So the Internet Protocol basically tells you which computer we're going to send it to, or which PLC we're going to send it to. And then the transmission control protocol tells it which application within the PC that we're going to send it to. And so that's these 4 different layers. So if you look at the TCP/IP model, they just give you those 4 layers. If you look at the OSI layer, they basically take the application layer and break it down into 3 different sections: application, presentation, and session. And they also take the hardware layer and break it down into frames and bits. Alright, so I just kind of wanted to do a little bit of a review here. Remember that your number system conversions, converting binary to decimal or decimal to binary, because when you're working with IP addresses, you are going to have to work with binary to decimal conversions, and you need to make sure you understand that. So this is just kind of showing you here. We have the decimal number. I should have a subscript 10 there, 242, which we're going to break down into binary. And so you remember, you can basically take 242, subtract, start from the left, start subtracting those. Now the nice thing about IP addresses is if it's a version 4, IP version 4 IP addresses, which are 32 bits. So they're 32 bits, but the 32 bits are broken down into 4 separate sections called octets, where each octet is only 8 bits. So what you tend to see is these 8 values, 128, 64, 32, 16, 8, 4, 2, and 1, show up a lot anytime you're working with like IP addresses and stuff, because we break it down into an 8-bit section. So the 32-bit IP version 4 is broken down into this 8-bit section. Alright, so remember that a nibble is considered 4 bits. Okay, so if you're doing octal is considered 3 bits. So here, this slide's doing octal, so we have 3 bits. And if we go to the next one, which is hexadecimal, then that would break it down into 4 bits. Okay. Alright, so but when we look at an IP address, as I said, IP version 4, so usually you'll see like IPv4. IP version 4 is an address is composed of 2 parts: the network portion and the host portion. And I kind of think of that, if you think about like a house address, you have the street that the house is on, and then you have the number that the house is. All right, and so that's kind of the breakdown between the network and the host. All right. Now, why this becomes so important is because when you look at this IP address, So when you look at, say, this IP address here, this IP address is broken down into, again, 4 octets. Each octet is 8 bits. All right, and then here, this is what the /16 indicates how many of these 32 bits. So this entire number is 32 bits. And this is telling us how many of those 32 bits are part of the network and how many of them are part of the host numbering. And so when we look here, we see that this is 16 bits. So it's saying the first 2 numbers, because this is 1 octet, that's 8 bits. This is the second octet, which is 8 bits. So the 2 together gives me 16 bits. So if I have this IP address with the /16, which is telling me how many bits are part of the subnet, then that's telling me that these 2 numbers, 10.15, are the subnet. Okay, so that are not the subnet, but the network. So the network is 10.14. And this one here tells me that the network is 10.14. So when I look at that, I can see that these 2 computers are on the exact same network. Okay, so these IP addresses are on the same exact network. However, if we flip and we look at these numbers again, but now I'm telling you that the first 24 bits are the network. So now when you look at this, you see that these 24 bits are the network. So if these 24 bits are the network, this one is 10.15.24 and this one is 10.15.23, but these are different networks. So even if we physically wired these 2 devices onto the exact same network, they would not talk with each other because they think they're on a different network. They're going to ignore the other computer. So 10.15.23 here is going to ignore this computer. Okay, so this 10.15.23.56, this computer here is going to ignore this one and vice versa because it thinks they're on a different network, even though they're wired. You know, I mean, you could have, this could be a PC with a crossover cable plugged directly into the PLC, and so they're wired directly together, and they will not talk to each other because the subnets disagree with each other. So that's why it's so important that you understand this network, the network portion, and how the subnet works. So here, the 16 tells us that the subnet, or the network piece, is just 10.15. And so these 2 would work just fine. So, like I say, if you had the case where you actually had them wired in with a crossover cable and these were the IPs, all you would have to do would change the subnet mask from 24 back to 16, and they would realize they're on the same network and would communicate. But if you had it set up with a 24-bit subnet mask, then they would not communicate. And so that's the key difference there, and that's why this subnet mask becomes so important. Because you're like, I've got these things wired together. There's nothing else. I got a crossover cable and I've got the PLC wired. I know the cable's good and it's hooked directly into the PLC, and they won't talk simply because of the subnet mask. And that's why that is so important there. Alright, so some of the devices, if we're using Ethernet, we have a switch. Now, years ago, you could go out and you could buy a hub. And a hub is kind of like a switch, only it's not quite as smart. So the switches are a little bit smarter, a little bit faster than a hub. and of course that means they cost a little bit more. But 30 years ago, a hub would be much cheaper than a switch. Nowadays you can't hardly buy a hub because most of the switches, the cost of the switches have come down, so people don't even mess with a hub. All right. But a switch will allow you to plug in kind of with a star topology as shown in the image here, where you can plug in multiple devices. They could be PLCs, they could be smart sensors, smart actuators, PCs, whatever, all wired into the same switch on the same network. But again, for them to communicate, not only would they have to be wired together, but they would have to know that they're all on the same subnet. They would have to understand that. And each one, didn't actually say that, but each one would have to have a unique address. If you put two of them on there with the exact same address, you're going to have, it may kind of work sometimes, but you're going to have conflicts. They're going to get confused who you're talking to. So they need to have a unique address on that network. A router, on the other hand, will allow you to route packets between different networks. All right, so if you have, like if we went back to this connection here, where these two are on different networks, you could still communicate between these two machines with these two addresses, but you would have to have a router set up. You would have to have a router set up that understands which of the network was which, and it can then route the packets of information through from one network over to the other. Now, when you're going between networks, then you also need to consider, is it a trusted network or is it the internet? Now, and of course, nothing on the internet can be trusted, so you would need to set up a firewall. A firewall is a security device that prevents unwanted packets from traveling in and or out of the network, depending on what you set it to do. So it could block all communications either way, or just allow communications that you want to allow. Now, a lot of times, like if you go and you buy a Wi-Fi router at Best Buy or something, you actually get the firewall and the router and the switch. It's all wrapped into one for a very reasonable price. And again, that's why we're seeing so much Ethernet devices even on industrial networks, because the cost has dropped so low, and also it's very high-speed networks. Right? But we do have to keep in mind this security thing. So as I said before, you should have your industrial network should be completely isolated and separated from all other traffic. You shouldn't have just people from China or Russia who could just connect directly to your industrial network with all its sensors and actuators and stuff, and possibly give false instructions and cause damage. So in one case of that, it's been quite a few years now, but there was a network called the Stuxnet virus, and this was used to physically damage the nuclear program in Iran. And so it actually specifically was designed to target like PLC type devices, and basically kind of confuse them and tell them that things were running well when things were actually getting too hot or something like that, to the point that the equipment got damaged. Alright, so we talked about protocols. Protocols are the rules that a particular type of network uses. How we encode the data and transmit that through pulses of light or pulses of electrons. And encapsulation is how we take the data and we basically wrap it inside the envelope and put addresses and that kind of information on it. And we talked about how important the network address, the IP addresses are, and the various devices that we need on the network.